Hi there, students. Welcome to lesson 16.1, Properties of Logarithms. This is Algebra 2B, and I'm Mrs. Brunk. In today's lesson, we're going to be exploring some properties of logarithms, and we're going to use some of these properties of logarithms to solve some real life problems involving exponential growth, exponential decay. So to start off, we're going to do a little exploration, and it's going to require you to use your graphing calculator and to pause the video. So I want you to take a few moments and pause the video and evaluate the expressions in each set using a scientific calculator. So set A and set B. And then what we're going to try to do is see if we can match up the expressions from set A to set B. But I just want you to complete this part first, and then you can tune back in and we'll kind of see if we can match those up together and see how they might reveal some properties we're going to learn about today. Okay, so clearly that little explanation revealed some patterns, or at least some connection between the two sets. And I can see that the log of 10 over e in set A matches up with 1 minus the log of e in the second set. And I can see that the natural log of 10 matches up with 1 over the log of e in set B. So this is kind of unusual anyway, seeing log with e. Usually you'd think of ln, or natural log with e, and 10 with log. So clearly there's some kind of angle with this activity that we're trying to get at. So then the next one, the log of e to the 10th power, and that one matched up with 10 times the log of e. So let's see if I can fit that in there. 10 times the log of e, and then finally the log of 10e, it was 1.434, and it matched up with 1 plus the log of e. So somehow these two expressions are equal to each other, and we're going to be exploring some log properties, and we're going to see if we can come back and figure out where these relationships came from, how the left side and the right side are in effect saying the same thing and how they're equivalent. So a logarithm is the exponent to which a base must be raised in order to obtain a given number. So that's something we've been establishing. We've been talking about that. So log b, base b of b to the m power is m. It follows that log base b of b to the 0 power equals 0, and so log base b of 1 equals 0. So that is actually one of the most basic log properties. We're also going to look at some additional properties, some that we've already been kind of using, we just didn't have a formal statement of them, and some that will be new, including a product, a quotient, and a power rule for logarithms. And that may lead you to think about some of the properties we learned when we studied exponents. So we'll kind of try to see if we can make that connection. So first of all, we're going to take a look at what are called definition-based properties of logarithms. And the first one, I think probably the one that we've used most often, was the middle one. The log base b of 1 is equal to 0. So remember, what that's really saying is if you take this base of b and you raise it to the 0 power, you'll get 1. Remember, that's true of every single base, because it doesn't matter what the number is, as long as it's not 0. If you raise it to the 0 power, you'll always get 1. Now the next one is log base b of b is equal to 1. And what that's really saying, remember, is if the base is raised to the first power, we'll get the same thing. So in other words, b to the first power is equal to b. So that would be true no matter what the base was. If it was, say, log base 2 of 2, that would have to be 1 also. Log base 5 of 5. And that's exactly why the log of 10 is actually equal to 1. And that's because that really means log base 10 of 10. And the ln of e is also 1. And that's because that's really like saying log base e of e. and anytime the base and that result match, the exponent has to be 1. Because that's the only way we get we get the exact same thing as the base is if we're raising it to the first power. And then finally, as far as the definition-based properties, there's log base b of b to the m power is m. And that's really clear if you just look at kind of switching it to exponential form, how that has to be the case. So that's like saying b to the m power would have to equal b to the m power. So, clearly that is true as well. Now, the next property we're going to learn is called the product property of logarithms, and it kind of comes back to the exponent property that's also called the product property of exponents. And here's an example of that. So if I had x to the third times x squared, we know that in order to combine them together, they have to have the same base, which they do, and when they do, then we go ahead and add the exponent. So that would be an x to the fifth power. So because a logarithm is an exponent, it's like, it's written in, the inverse. We're actually going to look at this property in reverse. And the product property for a logarithm, so product property for a logarithm basically says this, that if you're adding two logarithms with the same base, you can combine them together by just simply multiplying the results and rewriting it as a single log with the same base. So log base b of m plus log base b of n is equal to the log base b of m times n. So in other words, when you're adding logs that have the same base, you multiply them together, and which is the reverse of what we just said here with the exponent property. Let's go ahead and turn the page and let's look at an example of applying that property, and then we'll come back and learn the next one. So let's go ahead and flip over to the next page. And we're going to take a look at an example of using that product property. So example B is a product property for logarithms, and I can tell that because it's a plus, right? Plus is associated with product. I mean, actually plus is associated with sum, but the product rule is used when we are adding two logs that are the same. I'm going to make up a little different example to go with this first. So if I had the log base say 6 of 4, and I was adding that to the log base 6 of 9, and if I did not have this property, I would have to look at this and say, okay, well, let's see, this first part, log base 6 of 4. So that's like asking, what power would I have to raise 6 to get 4? And boy, I sure have no idea what that is, because I know that 6 to the first power is 6, so it's got to be something less than 1, but greater than 0, because 6 to the 0 is 1. And I could sit and guess and check different, like say 6 to the 0.5, to the 0.6, to the 0.7, to the 0.8, and so on. I'm just trying to kind of narrow it down, but this is certainly not going to be an integer, or at least not, as far as I can tell, a really like a simple kind of fraction that I would just be able to tell mentally. And the same thing goes for log base 6 of 9. But when I use this property, I could combine these together, and I could say that this is the log base 6 of the product of 4 and 9, which is 36. And now this says log base 6 of 36, and I know, for sure the value of this one has to be 2. And that's because 6 raised to the second power is 36. So that's an example of when, that's the most helpful, the product rule is the most helpful, is in situations like this. Now, in the case of example B up here, I could have evaluated these two things separately. I know that the log base 5 of 1/25 would have to be -2, because 5 squared is 25, and put a negative on it, it takes the reciprocal. And I also know that the log base 5 of 625 is 4, because 5 to the 4th is 625. So it looks to me as though this sum of these two logarithms should be 2. And so, I can confirm that when I use this log property. So, but combining them together using the product property would be the log base 5 of the product of 1/25 and 625. Well, 1/25 times 625 is 25, and I know that if I raise 5 to the second power, I'll get 25. So that confirms I can check my answer along with being able to, in the original, it turned out that those were, values I could have figured out mentally separately, but then combining together, I can confirm that, in fact, the log base 5 of 25 is 2, and so is the log base 5 of 1/25 plus the log base 5 of 6/25. So that's an example of the product rule. Let's go back and look at the next property. So in the next property, we are going to be looking at the quotient property. So the quotient property for logarithms relates back to the exponent property of the quotient property. So the quotient property for exponents looks like this. Let's say I had x to the 5th, and I was dividing it by x squared. I know that that's x to the 3rd power. And I got that by subtracting the exponents. But the bases were the same, and so when I was dividing, I subtracted the exponents. Well, using the quotient property of logarithms, we would do the same thing when we're subtracting two logarithms with the same base. We can combine them together by using the quotient. So you can see how these properties are working in the reverse, and because the logarithm is the inverse of an exponential expression. So that just means if we want to combine them together and they're two bases that we're subtracting with the two logs with the same base that we're subtracting, we can combine them together into a single log by finding the quotient between those two results. Let's go look at an example on the next page. So example A is an example of using the quotient rule. I'm just going to title this quotient. And again, there happens to be two values that are fairly reasonable to just evaluate on their own. So I can check my answer. So I know the log base 3 of 27 is 3. I know that the log base 3 of 81 is 4 because 3 to the 4th is 81. So I know that when I combine these together, I should get a -1 when I find the value, because 3 minus 4 is -1. So combining these together using the quotient property, I'd write it as the log base 3, still the same base, but this time I'd have to divide 27 by 81. Well, off to the side, I'm going to do that because I know that reduces. So 27 divided by 81 turns out to be 1/3. So this is like saying the log base 3 of 1/3 is what? Well, I know that raising something to the -1 power is going to take the reciprocal, and since 1/3 is the reciprocal of 3, that must be the case here. So there I wrote it as a single logarithm, and I found the value of -1 for the exponent. And again, because the original problem was one that there were reasonable values I could figure out, I was able to confirm that, in fact, the difference between those logs is -1. So I want to real quick go back and take a look at this little table that's investigating the properties of logarithms, this part B. And right here where we found that the log of 10 divided by e was 1 minus the log of e. Well, this is actually using that quotient property in the reverse in order to, like separate them off into separate logs. And so I know that what this has to equal is the log, of course that's base 10, of 10 minus the log of e. So I just went in the reverse, I used that property in reverse, and I know that the log of 10 is actually 1, so I could change this to just be 1, and that's where the 1 minus the log of e comes from. And similarly, you could do this that with the product rule, and that's where this comes from. Because again, we have a log of 10 times e, we could rewrite that as the log of 10 plus the log of e, again using that product rule in reverse, and then the log of 10 is actually 1 because that's log base 10 of 10, so that's 1, so that's where the 1 plus log of e comes from. Let's go ahead and take a look at the next log property. So the next log property is, I think, probably one of the most important log properties, at least in my mind, and I use it the most, especially in this lesson. And that's the one that we use to solve a lot of these equations we're going to solve. It's called the power property of logarithms, and let me remind you of a similar property when it comes to exponents, like the related one, and that was when we raised a power to another power. So when we raised a power to another power, for instance, if we had, say, x squared to the 3rd power, we would just simply multiply the exponents, and it would be x to the 6th power. So raise a power to a power, you multiply. Well, remember, a logarithm is a power. It is an exponent, right? It's just written from the other perspective. And so what this property says is that the log base b of m to the n power is the same as n times the log base b of m. And so you can probably tell that the only thing that changed from the left side to the right side is they took this n, this power, they brought it down in front, and they turned it into a coefficient, and they wrote it as n times the log base b of m. And so they took it from being a power, which is a logarithm, this in this case, that was being raised to another power, and they turned it into multiplication, which is, again, using the exponent rule in reverse. Let's go ahead and take a look at an application of that, or an example of that. Turn the page. Okay, so looking at the your turn example, log base 4 of 64 to the third power. Now, if I were not to have this property, what I might have to do is I would have to look at this and say, well, I have to find a way to get the 64 to have the same base as the logarithm, which is base 4. So maybe I could say, okay, well, that's log base 4 of, and then I'm going to write 64 as a power of 4, and it's 4 to the third. But then that was being raised to the third again. And so then that would simplify down to the log base 4 of 4 to the ninth power, because when you raise a power to a power, you multiply. And so then I could tell that my answer, or my value of this logarithm, is 9, because then 4 to the ninth would equal 4 to the ninth. Now, using this power property instead, I could have just looked at this in its original form, said, oh, there's an exponent there on that logarithm. I'm just simply going to bring it down in front and turn it into a multiplication. So that would be 3 times the log base 4 of 64. And then I could go ahead and evaluate this log base 4 of 64, because I know that that part is saying 4 to what power is 64, and of course that's 3. But then now I bring that 3 down, and that's saying 3 times 3, which is 9. And so that's a way of using that power property to evaluate a logarithm that's a little more complicated, that we would have to instead utilize some of these other exponential properties in order to simplify it otherwise. Okay, so now we are down to one more property, so let's go back to the properties page, and let's take a look at the final one. The final one's called the change of base property, and that one is one that I've already kind of talked to some of you about. Those students that maybe had the older calculators that didn't have the key that allowed you to change to whatever base you wanted, and just had the log key and the natural log key. The change of base property says, you know what, you can change a logarithm to any base. You could change it to base 2 or 7, or why not 10? Why not e? Well, base 10 would be really nice if you used base 10, because your calculator has a base 10 key and also a natural log key. So let's say, for instance, you had the log base, I don't know, 2 of 7. And this is not going to be one that's just real, that we're going to be able to figure out, easily, because it's not going to be an integer. The closest we have is 3, because 2 to the third would be 8, right? So it's going to have to be a little less than 3. But instead what we could do is we could write it in whatever base we choose. So let's say we chose base 10, and we could rewrite it as the log of 7. So again, I'm implying it's base 10, divided by the log of 2. And that allows me then to go ahead and use my calculator and just divide the log of 7 by the log of 2. And when I did that, I got about 2.807. And that makes sense, because I knew it was going to have to be just a little less than 3, because I know that 2 to the third is 8. So this is really helpful when you come across a logarithm that is very difficult to evaluate mentally. And that actually leads us to the final example on the next page. And so we turn back over and take a look at that. So this one log base 8 of 18 minus log base 8 of 2, well, this actually is going to require us to use two different properties, because right there I see a subtraction, so that's the quotient property. I can rewrite this as a single logarithm, as the instructions go, of still base 8, of the quotient between these two, so the quotient between 18 and 2 is 9. But now I have to answer this question, 8 to what power is 9? Well, it's going to be a little over 1, but I don't know exactly what that is. And I can now do change of base and rewrite this in base 10 as the log of 9 over the log of 8. So what the original base was, it stays on the base. It goes down to the base, or the bottom, or the denominator. And we can simply type that in the calculator as the log of 9 divided by the log of 8. And that's about 1.067, about 1.057. And I can check that by saying if I take 8 and raise it to the 1.057 power, what do I get? And I get 9.006708, and so on. And so it's about as close as I'm going to get there to raising 8 to a power and getting 9. So that's called the change of base property, and again, that's handy in cases of things that are just not easy to evaluate in whatever base they are to begin with. You can change it to whatever base that you want. Now, one other situation you might have used the change of base for is, let's say you had the log base. Let's say you had the log base, say 8 of 32. And I mean, you could use base 10. You could even use natural log. I mean, you can change to whatever base that you want. But another thought is to see if you could try to find a base that sort of, is a natural fit for what these two values are, for the 8 and the 32. And when I think about 8 and 32, I automatically think of powers of 2. So maybe I'll change it to base 2. So I could say the log base 2 of 32 over the log base 2 of 8, and then I could evaluate those separately. So the log base 2 of 32 is, of course, 5, and the log base 2 of 8 is 3, and so I get 5/3, which is like saying 8 raised to the 5/3 power is 32, and I just confirmed that on my calculator that that is, in fact, the case. So that allowed me to find the exact value as a fraction instead of what I would have gotten had I typed it in my calculator with, say, base 10 or natural log, would have been 1.6 repeating. And I mean, of course I know that that is 5/3, but by using a base that's common to those two numbers, 8 and 32, I was able to, really kind of evaluate this without even using a calculator. So that's nice. So now we're going to move on to the real reason that we study logarithms and exponential functions, and that's to solve real life problems. That's the whole point of math, is really to describe real world situations. So we're going to be looking at rewriting a logarithmic model in order to solve it. So there are standard formulas that involve logarithms, such as the formula for measuring the loudness of sounds. The loudness of sound, L of I, in decibels is given by the function L of I is equal to 10 times the log of I over I sub 0, where I is the sound's intensity, whatever the sound you're trying to measure the decibels for, per watt, or in watts per square meter, and I sub 0 is the intensity of a barely audible sound. It's also possible to develop logarithmic models from exponential growth or decay models, such as f of t is equal to a times 1 plus r to the t power. So those are the ones we've been looking at, like for say annual growth of money or something like that. Or the decay model, a times 1 minus r to the t power. And we can use these strategies and these properties and things like that to solve problems like that. So let's first look at this example of this concert and the sound level at the concert. So during a concert, an orchestra plays a piece of music in which its volume increases from one measure to the next, tripling the sound's intensity. find how many decibels the loudness of sound increases between the two measures. Now the problem here is we're not actually given the intensity of the sound of either one of these measures. Okay, so we just know that the second one is 3 times as loud as the first one. And so we want to know the difference between them. So it says let I be the intensity in the first measure, so 3I is the intensity in the second measure. So plugging those things into our formula would look like this. So the first measure, so the difference between, I guess the difference between the, that's not necessarily maybe the first, but the higher one, I guess is what I'm really saying. I don't know if it was necessarily the first because it sounded like it was low, then it went high. So the higher one, and then the lower one, and we're going to subtract, right? So the higher one is 10 times the log, and of course that's base 10, of I, or actually the highest one would be 3I, 3 times the intensity over I sub 0, and then minus 10 times the log of I over I sub 0. Now, first of all, I see those 10s out in front, and I know that that is a greatest common factor of those two. So I could just simply take that 10 out, and that leaves me with a difference between two logs. So the log of 3I divided by I sub 0, and it might bother you that you have all these apparent variables here, but that's all going to work out in just a second. And even though we don't technically know what I is, or really even haven't been reminded what I sub 0 is. So I recognize here this is the quotient property for logarithms. So if I were to take, and first of all I have that 10 out in front, but then I'm going to combine those logs together into a single log, and I'd have to do that by, I'm going to divide these two things. Well, I'm just going to kind of go off to the side and show you what that looks like when I divide those two things. So when I divide 3I over I sub 0 by I over I sub 0, that's like saying I'm going to change that to multiplication of the reciprocal. So I'll just kind of rewrite that. So now that actually flips that denominator and makes it I sub 0 over I, and now it's multiplication, and now I can just simply cancel out the two i's and the two I sub 0's, and that just leaves me 3. So I go to put that back over here in my quotient, that just becomes log of 3. So that's 10 times the log of 3. Now I can just go straight to my calculator and type that in, and 10 times the log of 3 is about 4.77, and that's decibels. So that means that the higher measure was 4.77 decibels higher than the lower measure. So that's an example of how we can use a quotient property to solve an equation involving logarithms. Let's go ahead and turn the page, and now we're going to take a look at using the power property. So this is a problem we have actually already solved before. Maybe not this exact scenario with these numbers, but we've solved quite a few problems like this already using our graphing calculator method. So the population of the United States in 2012 was 313.9 million. If the population increases exponentially at an average rate of 1% each year, how long will it take for the population to double? So they want the population to double. And so kind of going back to our exponential growth model that we usually use right here, I know that we know what the starting population is, and we know that that is 313.9 million. We know that the growth factor is 1%, making this 1.01. T is what we're trying to find out the number of years. And we want to know when it doubles. Well, if I double that 313.9 million, I get 627.8 million. So what we had done in the past is we would simply just take and we would put one side here in y2 and the other in y1, And then we would use that intersection function and we would see where they crossed. But since this is an algebra class, we probably should be solving these algebraically. And so how do we do that? Well, the first thing is what we're trying to do is we're trying to eventually solve for t. And it's part of this exponential expression 1.01 to the t power. So our goal would be to first try to get that all by itself. And so to do that, this is actually multiplication between these two. So I'm going to undo by dividing. And I'm sure it is not surprising that when I divide 627.8 by 313.9, I get 2, because the whole point of the equation was to see when it doubled, right? And so we know it's equal to. So we want to know when the growth factor raised to the t power is going to be equal to 2, in other words, when it's doubling. If we want to know when it's tripling, that would be 3, and so on. So how do we solve that? Well, you know how we just divided both sides by the same thing, right? In equations, you can divide both sides of an equation by the same thing. It's still equal. You can raise both sides to the same power. You can, like, say, square root both sides. You can add the same thing to both sides. Well, you can also take the log of both sides. And why would I want to do that? Well, watch what happens when I take the log, and you can choose any base, but of course my calculator does base 10, so I'm going to use base 10. And in this case, and I'm going to take the log of both sides. Well, when I take the log of both sides, now all of a sudden, you know, logs have this great property, that says if you have an exponent on a logarithm, you can turn it into multiplication just by bringing it down in front. That's our power property. And so this would be rewritten as t times the log of 1.01, and then it equals log of 2. Well, now we're ready to solve, because t is being multiplied by the log of 1.01, so now I can just simply divide both sides by the log of 1.01, and I'm ready to go to my calculator to find out what t is. But instead of using the graphs and finding where the graphs intersect, I'm actually using algebra. And I'm going to just simply divide the log of 2 by the log of 1.01, and I get about 69.7 years. And I could verify that by plugging that back into my original equation and seeing if I plug that in for t, if I get approximately 627.8, and I do. And so this wanted to know, like, how long after the year 2012. So if we rounded that up to 70 years and we just added that to 2012, we'd have 2012 plus 70 years, or the year 2082. So I guess we'll have to wait till then to find out if the population doubled by then. So we'll leave this last question as a you try question, and that'll be one that we'll kind of touch base on in class, and we'll see how you do. So give that one a try. We're going to end the lesson here, so you'll have to come to class to find out the answer to the U-turn question and to check your work. So thanks for coming to class.